So yeah, it's a bit of a mouthful, but effectively what I want to tell you about today is some of the work that I've been doing around both machine learning and non-adiabatic dynamics towards 2D electronic spectroscopy simulations for these chromophores dissolved in solution and broadly applicable to a lot of condensed phase environments. But before I get into the details, I want to tell you very broadly about kind of what I've been doing in my PhD. There's, of course, the 2D electronic spectroscopy that I'll dive into more details where um, first I used machine learned potentials in order to train ground state dynamics and then also calculate electronic excited states. And we'll talk about that in much more detail today. And then one of the key limitations of this method is that the approximations we make effectively neglect all of the non-adiabatic dynamics. And there are a lot of cases where that's what's really interesting about photosensitive and photodynamics. And so recent work I've been doing with David Manilopoulos and people in his group has been to develop efficient Ehrenfest schemes for doing this and incorporating some of these non-adiabatic dynamics back in. In addition, I have used and developed a fermionic mapping approach. So based very much in kind of the world of Meyer-Miller mapping variables for fermions now, and applied this to model systems for interfacial electron transport. It's very early work, but kind of promising in direction for continuing to develop electron transfer and the non-adiabatic dynamics involved there. And finally, the last piece of my PhD has been working with a host of experimentalists through this National Science Foundation Center, where we were largely interested in interfacial ionics. So ion transfers between and to interfaces, where I used some enhanced sampling and classical molecular dynamic simulations in order to identify some of the key structural features involved in liquid-liquid proton transport, mediated by these proton acceptor molecules that sit on the interface, and the way that the dynamics of this interface really affect the thermodynamics of the proton transfer process. And then lastly, looking at a graphene conjugated surface where the sort of generally considered innocent counter ions that you add in order to make your solution conductive really do quite significantly affect the thermodynamics of proton coupled electron transport to that proton coupled electron transfer to that surface, and the role of exactly what those ions are doing. But to focus today on optical spectroscopy in the condensed phase, we're of course interested in all sorts of phenomena, including things like how photosynthetic bacteria can manage the energy transport and track the dynamics of where energy is going to the photosystem and to the reactive center. But before getting to sort of really complicated systems like that, the method that we were looking at and developing, we wanted to start with a base test where we considered this very standard Nile blue chromophore. This, for experimentalists, is one of the classic tests of, I just built my new laser system. Am I getting the results that I expect? For us, this is the same thing. We're using this as a test model that's relatively straightforward and gives us a good assessment of how well the theory and the methods that we're developing work. And so the 2D spectroscopy that we take a look at, these third order response expressions involve a 3-pulse sequence where each pulse is separated by a time delay, first T1, and then a second T2, and finally, as you watch the emission of this molecule, a third T3. And so what you end up getting is this time series at different T2 delays, mapping the excitation along the x-axis of the Fourier transform of this T1 and the emission along the y-axis to track how the energy is moving as you go from short time delays out to long. And so we'll look at a couple of features involved in this. But from a mathematical perspective, what we're really looking at is this third order response function and taking apart all of these commutators, you end up extracting sort of this Fourier transform expression that I talked about, and have a whole series of these terms that are associated with specific physics, like stimulated emission and ground state bleach processes. But how does our method in particular work? We're not directly simulating the time-dependent electronic fields. We're treating this as a sort of weak field limit where all we're interested in is the correlation functions of the energy gap fluctuations. And so what that ends up looking like is, for this Nile blue, we sort of theoretically hit it with light by just applying a dipole operator to the density matrix that models the system. And for Nile blue, we only really have to worry about two electronic states. And so we can run purely ground state dynamics by taking the second order cumulant approximation to the energy gap correlation function. And this then gives us a way where we don't have to run explicit excited state dynamics. This is also where we start to neglect the non-adiabatic effects, because we're not getting the energy transfer between these two states. And so instead, we're assuming that these are well separated and it's only the light that's coupling between them. We then, at each time point in this trajectory, calculate the excitation energy. So it's just the direct Frank-Condon excitation using TD-DFT, and get this long trajectory of all of these energy gaps, which you can then calculate a correlation function from, and ultimately down the line get linear as well as 2D spectra just from this one correlation function. Now, of course, doing that with DFT and TD-DFT for every single configuration is still very, very expensive. To put this into context, if we consider this Nile blue molecule and two solvation shells, so two layers of ethanol around that molecule, that gives us about 1,000 atoms. And a TD-DFT calculation for that size of system using 4 NVIDIA A100 GPUs takes about half an hour just to get the energy difference between the two. If you want to do that for an entire correlation function, you need tens of thousands of these. And if taking, for example, just 25,000, that's on the order of 50,000 GPU hours and the length of an American PhD, which really is much too long for us to be practically doing these things on a routine basis and collaborating regularly with experimentalists. Even if you can parallelize this, of course, that's a lot of compute resource to commit to just a single system one time. And so the eternal question that we've been all asking about all sorts of things in science, especially, can machine learning help? And in order to answer this, we focused on this equivariant transformer architecture, where this is a purely local model. It's taking in the local environment around each atom and using multi-head attention mechanisms in order to learn atomistic contributions to the ground to excited state energy transfer. We train with both that energy difference and then as well the gradients on that difference surface. And it's really the gradients that give us the amount of data you need to get a useful model. And so it really does work quite well. With just about 100 TD-DFT calculations, we can train a model that in less than 300 GPU hours now is effective and very efficient at going back and calculating the rest of the 25,000 configurations that you need for the full trajectory. We use the same principle and process in order to take a step back and train a machine learning potential for the ground state dynamics. So we have two models, one for ground state dynamics and one for this TD-DFT replacement for the excitation energies. And so ultimately the question is, how well does this work? If we start by looking at the linear absorption spectrum, they agree quite nicely. So here the peak maxima are shifted to align perfectly. So that is a result of TD-DFT on its own, nothing to do with the machine learning. The functional that we use is well known to systematically overestimate these energy gaps. And so in order to get a useful comparison and to look not at the absolute energies, but at the way that the nuclear dynamics are coupling to this excitation, we just shift these over and then can look at broadening and the structure and shape of the spectra. And so that works quite nicely. We then transition to 2D spectra. And again, these, very broadly speaking, agree quite well. Again, from the beginning, Nile blue is a relatively boring molecule as far as interesting photophysics goes. It's just this 2-level, there's one peak, it moves a little bit. And so those kinds of things we get well, but we can take a step further to kind of identify some of the very challenging things for any 2D spectroscopy analysis that become just a little bit easier when you're pairing your experiment with a theory simulation like this. And so what I want to sort of test your eyes with is, as you look at this experiment, right below the very dark primary peak, as you look at later T2s, there's this feature that starts to grow in, something that wasn't there before and is probably just barely visible, especially to people in the back. This is also really hard to analyze quantitatively when you're dealing with the spectra, because it's effectively just a shoulder on the main peak, and sometimes not even that. The simulation doesn't really have a clear structure there. This is coming from a dynamic Stokes shift as excitation on sort of the system on its excited state starts to relax, and then at later times emit at a lower energy. And so you can look at this from a sort of double-sided Feynman diagram perspective, where you have contributions for this 2-level system from ground state bleach and from excited state, or from stimulated emission. And focusing right in on the T2 component, this is where the ground state bleach is evolving during T2 on the ground state, so you don't change the peak position, but for the stimulated emission, you do. And again, that's very hard to separate out from an experimental perspective because you can't observe one and not the other when running an actual experiment. But these are two different mathematical objects, and we can plot them separately and start to analyze them from a simulation perspective. And so when you do that, we now take just the component from the stimulated emission, and we look in kind of right around the peak maximum, zero in on where the peak position is by using a weighted average along the y-axis, this emission axis, and that gives us kind of an initial point at T0. You can then do this again and again for all successive T2s, and you get the dynamics of how the system is relaxing on the excited state implicitly from your exclusively ground state dynamics originally. This is effectively just kind of reweighting what sort of energies you have in order to give you this additional information. You can then do the same thing for the ground state bleach term. And again, these are, especially at later times, very asymmetric peaks. And so you watch and you track the peak, not the peak maximum, but the weighted mean of this peak. And that then gives you this slight shift up in the ground state bleach term. And at long time, this is then closely related to the static Stokes shift that you get just from looking at the difference between a linear absorption and a fluorescence spectrum, and the frequency shifts in those. I could go on and on about the kind of analysis and Fourier transforming these fluctuations or these oscillations and extracting information about exactly what nuclear dynamics and what nuclear vibrational modes are coupling to the electronic excitation and its then relaxation. Nile blue, again, we didn't learn anything particularly new and different about this test molecule, but these types of analysis are quite straightforward and very much available to anybody who is able to run some initial molecular dynamics, train these potential energy surfaces. Really, it's limited by the type of electronic structure that you can do for the excitation energies. And especially as you go to more and more electronic states involved, there are two dangers that will appear. First, the reliability of that electronic structure, especially something like TD-DFT, doesn't do as well for higher lying states. And second, you start to get cases where those electronic states are going to actually be much closer in energy to each other. They're going to be interacting with each other, and you really have significant non-adiabatic effects that this type of approach, these correlation functions based on ground state dynamics, just aren't going to capture. And so in order to address that, and come back to something more like a coupled set of chromophore molecules, we've been working with, as I mentioned, members of David Manolopoulos's group to incorporate Ehrenfest dynamics as a kind of next step up the rung of complexity in quantum dynamics. So here's a semi-classics method that is mean field and still very approximate in many ways, but is starting to capture the kinds of effects that we are interested in and still might be affordable for, and still is affordable for ab initio systems once you start kind of playing some games. The work that we did was just on model systems and model Hamiltonians, kind of building up a framework to do this. And so one of the key challenges that appears when you start simulating this with a semi-classics method is your initial condition is, for all of the dynamics, really a coherence state. If you think about starting your system in its ground state, hitting it with a laser pulse, where we then approximate that just as acting with a dipole operator, you get some expression that looks like some term of states where the bra and the ket are going to be different. And within Ehrenfest in particular, that introduces a choice where you have a very well sort of single choice for a pure state. There's one wave function that defines your system, and that one wave function then tells you what your force should be for evolving. When you have a coherent state, you now have these two wave functions that are coming together to give you your state. There is no one wave function that tells you what's going on, and that therefore introduces the opportunity to make different decisions. And so I'm just going to talk about two possible choices that one could make. There are many others, and there's still kind of open opportunity for thinking about what the most effective is, because they give different ultimate results, even though on paper they look like they should be the same. And so taking this a step further, if we have some initial condition coherence, one can write down, honestly, arbitrarily many decompositions of that state in terms of pure states. And in particular, we can look at a couple of these. So if you plot this on something like a block sphere, where now you have states A and B contributing the north and south poles, and linear combinations of the two along the rest of the block sphere, you can pick any number of points and combinations that give you a sum that comes back to this original AB state. And so members of Tom's group a few years ago proposed what we've been calling this polar decomposition, where you include the two states on the poles and two states on the equator to give you, with these particular weights, a sum that gives you back this desired coherence. And then you run at each T2 delay, or rather at each time you apply a dipole operator in the simulation of the 2D spectra, you then branch into this new set of four states. And so because there are three dipole operators acting followed by dynamics in a 3-time correlation function for 2DES, that means taking what was once just a single correlation function and a single trajectory into 64 components. And that becomes much more expensive, but does quite well at giving you reasonable results for a number of the systems that they tested in this paper. What we were finding, however, is that there are limitations to this, and you can definitely do better. So if instead you rewrite a mathematically equivalent decomposition, now 4 states on the equator with these definitions for wave functions and weights, you actually get a really clean symmetry that means that was once 64 branches, only these red components are actually necessary for the equatorial decomposition. The T1 and the T3, when you're evolving these coherent states, you can analytically resum the decomposition of these pure states, and you get a 16 times faster code, as well as something that I'll show you in a moment gives much more accurate results. So here now, we're looking at a Biexciton model. These are just a pair of coupled 2-level systems, and the HEOM exact results compared to this equatorial dynamics and polar dynamics. This is not a issue of failing to converge the polar, but that one choice versus the other does genuinely give very different nuclear dynamics or vibrational dynamics, and that makes a difference in the ultimate 2D spectra that you predict. The only other piece, there's quite a bit in this that I could talk about, but the other piece that I want to highlight here is that these methods are very efficient. The moving to something like an FMO model, where now you have 7 coupled dimers, we're able to, with this equatorial mapping or equatorial decomposition, get very nice comparisons to Ehrenfest or to HEOM when we fully converge, but even at just 2,000 trajectories, quite cheap in the grand scheme of a lot of semi-classics methods, you still get very nice results. You're able to extract a lot of the same information, even if it's a little bit more noisy. And so this gives us a lot of excitement for applying these things to ab initio models and ultimately to machine learning. And so, of course, I would not be here without the support of so many people, all of the members of Tom's group, past and present, as well as quite a few collaborators, especially Mano's group, for the Ehrenfest work together. Thank you all.
Yeah, thank you for this really interesting talk. Are there any questions in the audience? If not, let me start.
Yeah.
On slide 6.
Sure.
Right. We kind of see a pretty good, and I'm surprised how good kind of the agreement between the simulated and the experimental line shape is. Is this purely due to kind of the finite temperature fluctuations which you capture in the simulation, or is there anything like Frank-Condon principle where you kind of excite, or where you take into consideration the overlap between the ground state and excited state wave function to kind of have a repeat broadening due to excitations of excited vibrational states in the excited electronic state?
Yeah, so you definitely get a lot of help from being in a condensed phase for these things. The 2D spectra of something like the Nile blue chromophore just in a gas phase would be much more structured. And so there's a lot of broadening that happens just as a result of being in a thermal bath. And that makes it a lot easier to get kind of reasonably good agreement. I will say these simulated spectra, you do have to be careful with a few things in order to get something that aligns well. In particular, the laser line width experimentally is relatively narrow compared to even sort of this energy range. And so you only have a small window where the experiment is actually exciting energies and going to get any non-zero signal. And so we have to effectively post-process the simulation in order to also give a smaller than the entire window of breadth of what could be excited, sort of fundamentally in nature.
Yep. I guess just for the context on this thing, right?
Yeah.
Do you know how accurate experiments can be?
Yeah, so it depends on how you measure accuracy, of course. There's a lot of kind of fine details that go into getting from a direct experimental output. Working with our collaborators on this, it really is incredible how much goes into getting these to work effectively. And so there are things like I use the laser pointer on here, that way people on Zoom can see too. This kind of blue feature that appears in the experiment is our collaborators attribute to effectively residual phasing noise. So in order to get this is the real component of the signal. In order to break apart the real and the imaginary component, you have to experimentally measure with an additional local oscillator laser pulse, and extracting back out the phase from that is still a very messy process. And so you get a little bit of loss in exact confidence coming from not quite perfectly removing that. And so accuracy to the extent that this is the expected shape, there shouldn't be significant off-diagonal features in this particular spectrum. You really have to kind of be comparing 2DES measurements against a whole bunch of other experiments in order to kind of develop a confident picture of exactly what's going on.
Yeah. I have a quick question regarding the machine learning architecture.
Yeah.
So I think you said you use essentially two models, both transformer based.
Exactly.
What was the main motivation for like using a transformer based model, and do you think it's transferable, the kind of knowledge that
Yeah, oh, absolutely. So this is one of many iterations we've gone through. A lot of earlier work in the group used home-built code that was based on symmetry adapted functions for these atom-centered descriptors, and just sort of a neural network model built on that. Those were a lot less data efficient and required on the order of 600 to 1,000 Nile blue configurations in order to train. And again, because it was kind of very home-built code, it was practically slow, not because the method is slow, but just because what we had was slow. And so this was transitioning to TorchMDNet, which has a lot of really nice functionality and was really effective for this project. More recently, a postdoc in our group has been working with a bunch of MACE models and sort of starting with foundation models, fine-tuning those, or starting just from scratch with a small foundation model and training with the same data set, and finding very similar results that with not very much data, she's able to get very reasonable potentials and all of that. And honestly, the ground state dynamics with a MACE model is more efficient than the ground state dynamics with this equivariant transformer. We needed about 2,000 configurations for ours. Probably could have optimized that with some additional clever techniques, but you can get even lower with MACE models. And so definitely exactly what your architecture is matters a lot less than having good data to begin with. Yeah.
Can you go to the slide where you compare the polar and the equatorial decomposition results?
Yes.
Yeah, this one. Yes. Okay. So you're saying that the equatorial and the polar decomposition, despite being mathematically like similar, get you different results. So do you have any idea why? And
yeah.
Why do you trust yours more than the polar?
Yeah. So all of these, the kind of ground truth as far as we're concerned is the HEOM. So this top line is an exact dynamics method. And so comparing to that is our baseline, who's right. And so from that, especially kind of right here in the middle where you're getting these really intense kind of negative features that shouldn't be there. And so as far as why one is better than the other, both methods, when you get to this picture, the four states add together to give you the same coherence either way. However, the forces that the equatorial dynamics generate are always on the exact sort of 50-50 balance of evolving a force based on the state according to wave function A and the state according to wave function B. And so this very cleanly, especially for the T1 and the T3 evolution, effectively reduced down to a mean classical path kind of picture. And so fit very nicely within sort of what you expect Ehrenfest to be doing. In contrast, the polar is this very unbalanced kind of averaging between the two. You also end up getting contributions from, I'm trying to think if I have. No, I don't have the figure in here. But you end up getting contributions where calculations of the stimulated emission peak, or rather of the stimulated emission term of your correlation function, have additional excitation from other sites that they shouldn't. And so there's some additional stuff and detail in there. The paper goes through a ton of detail about this, but I'd also be happy to chat later too.